Oh, hello there. I'm at the gym. I don't know why you're here, but I'm going to do some push-ups, so you can join me on the floor if you want.
Now, I'm not doing this just to show off or anything. I'm actually doing this for science, okay? Ugh. You see what happened there?
My arms moved, my shoulders moved, my back and stomach muscles moved, my heart pumped blood to all those different places. It's pretty neat, huh?
Well, it turns out that how we make and use energy is a lot like sports or other kinds of exercise. It can be hard work and a little bit complicated, but if you do it right, it comes with some tremendous payoffs. But unlike hitting a ball with a stick, it's so marvelously complicated and awesome that we're still unraveling the mysteries of how it all works. And it all starts with a marvelous molecule that is one of your best friends, ATP.
Today I'm talking about the energy and the process our cells and other animal cells go through to provide themselves with power. Cellular respiration is how we derive energy from the food that we eat, specifically from glucose, since most of what we eat ends up as glucose. Here's the chemical formula for one molecule of glucose. In order to turn this glucose into energy, we're going to need to add some oxygen, 6 molecules of it to be exact. Through cellular respiration, we're going to turn that glucose and oxygen into 6 molecules of CO2, 6 molecules of water, and some energy that we can use for doing all of our push-ups. So that's all well and good, but here's the thing. We can't just use that energy to run a marathon or something. First, our bodies have to turn that energy into a really specific form of stored energy called ATP, or adenosine triphosphate. You've heard me talk about this before. People often refer to ATP as the currency of biological energy. Think of it as an American dollar. It's what you need to do business in the US. You can't just walk into a Best Buy with a handful of Chinese yen or Indian rupees and expect to be able to buy anything with them, even though they're technically our money. Same goes with energy. In order to be able to use it, our cells need energy to be transferred into adenosine triphosphate to be able to grow, move, create electrical impulses in our nerves and brains, everything. A while back, for instance, we talked about how cells use ATP to transport some kinds of materials in and out of its membranes. To jog your memory about that, you can watch that episode right here. Now, before we see how ATP is actually put together, let's look at how cells can cash in on the energy that's stashed in there. Well, adenosine triphosphate is made up of a nitrogenous base called adenine with a sugar called ribose and 3 phosphate groups attached to it. Now, one thing you need to know about these 3 phosphate groups is that they are super uncomfortable sitting together in a row like that, like 3 kids on a bus who hate each other all sharing the same seat. So because the phosphate groups are such terrible company for each other, ATP is able to do this nifty trick where it shoots one of the phosphate groups off the end of the seat, creating ADP, or adenosine diphosphate, because now there are just 2 kids sitting on the bus seat. In this reaction, when the 3rd jerk kid is kicked off the seat, energy is released. And since there are a lot of water molecules just floating around nearby, an OH pairing, that's called a hydroxide, from one of the H2Os comes over and takes the place of that 3rd phosphate group, and everybody is much happier. By the way, when you use water to break down a compound like this, it's called hydrolysis, hydro from water and lysis from the Greek word for separate. So now that you know how ATP is spent, let's see how it is minted nice and new by cellular respiration. Like I said, it all starts with oxygen and glucose. In fact, textbooks make a point of saying that through cellular respiration, 1 molecule of glucose can yield a bit of heat and 38 molecules of ATP. Now, it's worth noting that this number is kind of a best-case scenario. Usually it's more like 29 or 30 ATPs, but whatever. People are still studying this stuff, so let's stick with that number, 38. Now, cellular respiration isn't something that just happens all at once. Glucose is transformed into ATPs over 3 separate stages: glycolysis, the Krebs cycle, and the electron transport chain. Traditionally, these stages are described as coming one after the other, but really everything in the cell is kind of happening all at the same time. But let's start with the first step, glycolysis, or the breaking down of the glucose. Glucose, of course, is a sugar. You know this because it's got an ose at the end of it. And glycolysis is just the breaking up of glucose's 6-carbon ring into 2 3-carbon molecules called pyruvic acids, or pyruvate molecules. Now, in order to explain exactly how glycolysis works, I'd need about an hour of your time and a giant cast of finger puppets, each playing a different enzyme. And though it would pay me to do it, I would have to use words like phosphoglucoisomerase. But a simple way of explaining it is like this. If you want to make some money, you gotta spend some money. Glycolysis needs the investment of 2 ATPs in order to work, and in the end, it generates 4 ATPs for a net profit, if you will, of 2 ATPs. In addition to those 4 ATPs, glycolysis results in 2 pyruvates and 2 super energy-rich morsels called NADH, which are sort of the love children of a B vitamin called NAD+, pairing with energized electrons and a hydrogen to create storehouses of energy that will later be tapped to make ATP. To help us keep track of all the awesome stuff we're making here, let's keep score. So far, we've created 2 molecules of ATP and 2 molecules of NADH, which will be used to power more ATP production later. Now, a word about oxygen. Like I mentioned, oxygen is necessary for the overall process of cellular respiration, but not every stage of it. Glycolysis, for example, can take place without oxygen, which makes it an anaerobic process. In the absence of oxygen, the pyruvates formed through glycolysis gets rerouted into a process called fermentation. If there's no oxygen in the cell, it needs more of that NAD+ to keep the glycolysis going, so fermentation frees up some NAD+, which happens to create some interesting byproducts. For instance, in some organisms like yeasts, the product of fermentation is ethyl alcohol, which is the same thing as all of this lovely stuff. But luckily for our day-to-day productivity, our muscles don't make alcohol when they don't get enough oxygen. If that were the case, working out would make us drunk, which actually would be pretty awesome. But instead of ethyl alcohol, they make lactic acid, which is what makes you feel sore after that workout that kicked your butt.
So your muscles used up all the oxygen they had, and they had to kick into anaerobic respiration in order to get the energy that they needed. And so you have all this lactic acid building up in your muscle tissues.
Back to the score. Now we have made 2 molecules of ATP through glycolysis, but your cells really need the oxygen in order to make the other 30 submolecules that they need. And that is because the next 2 stages of cellular respiration, the Krebs cycle and the electron transport chain, are both aerobic processes, which means that they require oxygen. And so we find ourselves at the next step in cellular respiration. After glycolysis comes the Krebs cycle. So while glycolysis occurs in the cytoplasm, or the fluid medium within the cell that all the organelles hang out in, the Krebs cycle happens across the inner membrane of the mitochondria, which are generally considered the power centers of the cell. The Krebs cycle takes the products of glycolysis, those carbon-rich pyruvates, and reworks them to create another 2 ATPs per glucose molecule, plus some energy in a couple of other forms, which I'll talk about in a minute. Here's how. First, one of the pyruvates is oxidized, which basically means that it's combined with oxygen. One of the carbons off the 3-carbon chain bonds with an oxygen molecule and leaves the cell as CO2. What's left is a 2-carbon compound called acetyl coenzyme A, or acetyl-CoA. Then another NAD+ comes along, picks up a hydrogen, and becomes NADH. So our 2 pyruvates create another 2 molecules of NADH to be used later.